Well, the Greeks held that the visual arts were the imitation of life, but the computer arts are the imitation of creation itself. Thank you very much.
My name is Severo Ornstein. I've fooled with computers for a little over 30 years. And in fact, I was at Lincoln Laboratory at about the same time that our next speaker was. So I've been asked to be the discussant for him. It occurs to me that hindsight is supposed to be easier than foresight, but actually, in my experience, hindsight is the hard thing. You get a bunch of computer people together arguing about which way things ought to go, and the arguments can be pretty fierce, but they don't seem to be ever as fierce as the arguments about how things did go. I suspect there's going to be more of this as time goes on today. We tend to think of history of a field, or at least I do, excuse me, as commencing more or less when we got into it ourselves individually. But of course, it's not really quite that way. Everything before was somehow a given when you came along. And so we're really only interested in history from the point where, excuse me, where we got into the field. But of course, that isn't so. Everything's got an antecedent. Last night I read through Doug's paper, and Doug and I, although we were at MIT at about the same time and at Lincoln, must have passed one another in the halls 1,000 times, but we never actually met until this morning. And but I was, of course, aware of his work. But in reading his paper, it took me back in a number of ways. First of all, it was lovely, of course, to run into familiar names. I think one of the reasons we're here is I think we like that a lot. Puts us in some sense in history. And there were all these very familiar names of people and places conjuring up all sorts of memories. Well, anyway, in the 50s, a lot of the ideas that underlie the work that has followed since were brewing in people's heads. And as I read Doug's paper last night, I realized how much of that there actually had to be. And we tend to think in terms of artifacts, it seems to me, as we look back. Whereas, in fact, what happens is some strange mixture of artifacts and notions and ideas and ways of thinking. And it appears that Doug really was very influential in sort of seeing what was available in the 50s and seeing possibilities growing out of that into the future. And the hardware, the things that he had available at that time looked very primitive, but the ideas were very, very far-reaching. And it seems to me the impact on what's happened is just enormous. And I really somehow, in reading his paper last night, suddenly realized how a lot of the thinking that was going on at that time was really very revolutionary. We take it all for granted now, but it really was very revolutionary at the time. Did you ever notice when you look at a picture of the old computers, ENIAC or something in that era, show people standing up in front of them? You ever noticed? One of the notions that Doug had was the notion of a partnership between a person and the computer. And of course, if you're going to enter into a partnership with somebody, you can't stand there all day long. You have eventually to spend a lot of time actually with the machine. It used to be that people sat down when they wrote programs, but they wrote them off somewhere else while they were thinking through the problem. And when they actually got to the computer, they stood there and someone took a picture of them so that we could all sit here today and look at those pictures. But in Doug's case, he actually envisioned this idea of a partnership. And as I say, in a partnership, you actually sit down and work at the machine. And so I like to think that what Doug has done is to make it possible for the rest of us to sit down. And true to form, he's here somewhere I can't see, and he's going to do that for me right now.
Great, thanks. I wish I'd met Severo many years ago, as you can see. That certainly was the most relaxed and flattering introduction that I've ever had. And I hope that the talk that I've put together will in fact live up a bit to the billing. But I have so many slides to go that I'm not going to try to follow the organization that's in the written paper. I'll instead try to follow pretty much a chronological approach. So could we have the first slide? And I'll just try to start out and use the slides as the outline for what I actually want to say orally. Now, this is actually my second round of trying to write up a bit of history that I was a participant in. The earlier one was in doing this history of programming languages, where I covered the apt system. And I'm well known, it's well known fact that I have a terrible memory for people, places, facts, or anything like that. So that when I'm asked to do this thing of cranking back into earlier times, I don't trust my memory a bit. But I have lots and lots of papers and artifacts and so forth. And so what I try to do is look for a theme that will carry through from the material that I actually have. I'm also not a historian, although I'm interested in having history captured. So I don't dare to put myself in the position of trying to write a tutorial or cover the field in general. Instead, what I do is I try to give a very personal view, almost an Edward R. Murrow approach, and only say things that I can actually find in my records themselves. And the interesting thing to me is that I always seem to come up with a few surprises, places where I've discovered that things are not as I remembered them, but I'm able to dig out how they actually were. So I have the next slide, please, which is just the title of the talk, A Personal View of the Personal Workstation, Some Firsts in the 50s. Now, I do this because I want to point out that I purposely have misspelled workstation throughout my paper. The reason is that I want to take as my theme that it's not just the workstation that's important, it's the personal work as well. And then the third component, the systematic approach to tying together the new mode of personal work with the features of the workstation, that systematic underpinnings of the software architecture would be our modern word for it. That makes the personal workstation as a whole, the PWS, is the third component of my theme. And the important thing to me is that, especially in the context of the early days of using computers, but also for the most part, and if you think of the fact that 80% of all the programs ever written still are those that are written in COBOL, the fact of using a computer personally is in fact quite a change in personal work habits. So that's my main theme. Let's get started on just the historical approach to walking you through why I'm up here talking to you. So we have the next slide now. The next slide is this one. This was my introduction to programming. I didn't write this program, Jack Arno did. This is the first program I ever saw. The thing is, I came to MIT straight out of Oberlin in this fall of 1951, and I needed a summer job for 1952. And I went to work at the Servo Mechanisms Laboratory, and part of what my work was working with results obtained with a mechanical autocorrelation computer that had been designed to the specifications of Norbert Wiener, had ball and disk integrators, an analog computer. And they were getting points that they didn't understand. When they set the very small separation, they got points that were way off the curves that they'd been getting before. And so somebody suggested that I check with Jack Arno, who they knew had written a small autocorrelation program for the Whirlwind computer. And this was the program that Jack showed me. In fact, his name is down here if you look very carefully. Next slide, please. So on July 7th, 1952, this is the actual application form filled out by John Breen to start the problem 87 on Whirlwind, where I first undertook to write my first program, which was a more elaborate autocorrelation program. And here's a copy of the printout. These are a little clearer in the, I guess I can't, this one isn't in the book. It isn't important, just to show that I'm only telling you stuff that's in my actual files. But the program was led to a whole string of things, including some of the work that Wes Clark mentions. Walter Rosenblith's group later on got started using the same autocorrelation program for some of their brainwave studies. Brainwave studies. Next slide, please. The important point is that the backbone of the history that I'm going through actually occurs in this collection of progress reports from Whirlwind, in which we, on a monthly basis, had to write up what had happened to our problem, so there's a good record of the things that I submitted at that time. Next slide. Next slide, please. And the key factor is that right after having started my autocorrelation program and running it, as this says right here, a shutdown of the Whirlwind computer was started August 11th and completed August 30th. My program wasn't even debugged yet. So I used that time period to write another program for Fourier transformation, which, so we could get power density spectra out of these correlation programs. And that later became the basis for my master's thesis and also was used for many other projects. But the important thing is that the reason for the shutdown was that they were completely revamping the input-output system for Whirlwind, putting in new instructions, SI for select input, SO for select output, RC and RD for record and read, and so forth. And the purpose was to attach the consoles and display lines that were needed for the air defense problem, which was the basis for Lincoln Laboratory, which was just then taking over the Whirlwind computer. Next slide, please. Now, the project that I was working on was concerned with airborne fire control systems, and in particular the evaluation of same. So down here we have a little bomber, and here's a fighter aircraft coming in to try to attack the bomber, and in the tail end of the bomber is a turret with servo mechanisms steering the guns and a radar dish flopping around, also gimbaled off of the guns. And so there was quite an elaborate set of angles that needed to be measured and ranges and so forth to see whether or not the fighter would be shot down by the bomber. And they had come up with a new form of air mass ballistic tables for high-speed calculations, and that was my first assignment in the laboratory. I had been teaching a section of calculus as a research assistant in the pure math program at MIT, but when I got bitten by the bug, and now I had two programs to debug, I was asked whether I'd like to make a career there at the lab in computers, and decided, gee, that would sure beat the pants off of just straight old mathematics. And so I've been there ever since on this path. So anyhow, it was the complexity of this problem of data reduction that was the background stimulus for all the work that I'm going to be talking about as the concept of the personal workstation built up and actually took place. Next slide, please. In fact, though, you see, that problem that I had to work on was so complicated that the first programming language I ever designed, I just threw this in because I ran across it in my file. The first programming language I ever designed was designed where the computer was a bunch of 6 or 8 part-time students at Marchant desk calculators doing the 139 steps to calculate this problem that we were trying to program for Whirlwind. This made our test case. So here you can see my little language of putting things into the accumulator and clearing the accumulator and multiplying and so forth. It was the people were the CPU for this first programming language of mine. Next slide, please. And just to track down the time as it goes along, this is actually a power density spectrum from my 1954 master's thesis, just to pin things down. And also, it shows with this tick marks along the vertical axes, making those little marks come out long and short, like they do on a ruler. That was, the next slide shows how I did that. Next slide, please. You can barely see it, but the whole program here is built out of nothing but SP and TA, that's subprogram and transfer address. That was the instruction pair that allowed call and return from subroutines on Whirlwind. And so I wrote the whole program for the logic of putting out the different length ticks in the proper order entirely out of those two instructions, which means that I was, unbeknownst to me, writing a finite state machine. And so I was very pleased with the elegance of it, but I didn't know what I was doing. Anyhow, there it is, along with the patterns of tick marks that would be given by different starting conditions. So that's sort of a measure of the coding patterns practice that was going on in those days. Next slide, please. Now, here is another view of whirlwind test control. The one that Gordon had in his talk was, as I said, from probably 1951 or very early 52. This shot was actually taken in 57, but I chose this one in order to show here the scope that we'll be talking about that was slaved to all the multiple scope lines that were put in for the air defense Cape Cod system. And down here, behind this thing, is another scope with this one has an automatic 35 millimeter camera mounted on it. And here's the photoelectric tape reader. Here's the flexorider, which at that time was used only for typing out and alarm conditions and monitoring results. The actual starting and stopping controls for the computer were mostly over here. Again, this was not a personal workstation because, again, it had an operator that actually was running the computer for you and stood in this area. All this other gear around here, by the way, is the marginal checking stuff. Next slide, please. Now, here is the master station, the mission director console location that was installed during that shutdown for use in the air defense airplane tracking problem. Now, as this is spelled out a little more clearly in the written paper, but at the time, the room was all painted black with black walls, and you walked in through a black set of drapes, and they had red lighting in there, and this whole room full of 24 or so such consoles scattered around glowing green phosphor. And so I make quite a thing in the paper about the impact upon me of finally getting the security clearance to walk into this classified area and see what had they actually done in changing over the Whirlwind computer, and could we use it for our very complicated set of programs that we were just undertaking to write. And so here is the Cape Cod system workstation with a scope, and these are vertical columns of buttons linked together so that 1 out of 8 can be pushed, and that would then set an octal digit. These are restart buttons so that you could take over the control of the entire computer from this particular station. This was the master station in room 222. Up here is the intercom and a clock over which you could communicate back to test control. And so I didn't know anything about using any of this equipment, but managed to hire Bill Wolf, who later on started Wolf Research and Development Corporation, who took over the whole computer, Whirlwind computer, lock, stock, and barrel when they moved it out from MIT. Bill had a Navy contract and kept it going for several years before it finally ended up in pieces around the place, including the Computer Museum and the Smithsonian. But the idea was that with this very complicated set of programs to control for reducing the data obtained from fire control tests, I wanted to have an actual interactive, this was just called MIV, manual intervention. I wanted to have manual intervention able to be used for controlling those programs. Next slide, please. There were more copies of this type of console, which was where a track initiator monitor worked for the air defense problem. And here you can see the light gun, as well as push buttons and a telephone and so forth. And notice, too, that these consoles were packed side by side, so that what we actually had was a console like this on the left and a console like I was just showing on the right, and that was the personal workstation area that we selected for using in our generalized way, rather than being a special application where the man in the loop was a required part of the problem in the air defense problem. We were trying to do it as a general purpose man-machine communication. Next slide. Just to show you the light cannon of that day, again, Gordon had the later version that worked with Sage system. In fact, this is actually Model 3 of the light gun for the early Whirlwind. In here was a photomultiplier tube with a lens system and a prism to pick up the light. Here's the little sighting target, and down here is the trigger. And as a matter of fact, in the written version of the paper, I didn't have the picture when I was writing that, and I didn't get to correcting it. I described these wires as coming out the top, but they actually come out here, of course. And what you do is you hold this with this barrel going back up over the back of your hand, and whatever spot the computer has just put into your target area, if you pull the trigger, then you signal by time only that that was the spot that you're interested in, and that's how they picked up tracking. Now, in addition to the light gun on Whirlwind, they also had a light cannon. In the next slide, we can get a far-off view of it. Way back here, if you just look, you can see a little box horizontal and a tripod that holds that box up in the air over a box that actually sits on the floor. That's the area discriminator. And this little box itself up here is the light cannon. The light cannon looked at the whole 16-inch scope at once, so that a spot put any place on the scope would be seen by this photomultiplier tube. And right here, these two airmen with their backs to us, by the way, are sitting at the actual consoles that we ended up using as our personal workstation. And by this time, later, all the walls have been painted light, and now they had the red lights and these upside-down lights at the top. But this is room 222. Now, the light cannon, when we first got in to see this room, I almost didn't register what it was. But then, as the next slide shows, as I was returning from an August 9th, 1954 meeting, flying on the airplane back from Texas with John Breen from the pre-B-58, the fire control system that we then were focused on was the tail turret for the B-58 Hustler supersonic bomber that was then not built, in the process of being built. And so we were called the pre-B-58 tests. And Emerson Electric Military Physics Research Laboratory in Texas and MIT were responsible for the evaluation of this set of equipment. And so as I was coming back from this meeting, I had been impressed by the difficulties that we anticipated in recording some 30 or 40 different quantities in the air, recording them on a very crude 1-inch wide flyable magnetic tape, which then would be played back into an 1103 computer on the ground at Eglin Air Force Base. And I was impressed by how unreliable all that was going to be. We were going to lose digits and data all over the place. And telemetering was so much worse in those days that we couldn't commit this very expensive program to try to use telemetering. We had to use the tape. And so I was flying back from Texas, and I had this vision that I'd like to be able to plot out the raw data that we were about to reduce in our programs, and if there were problems, I'd like to be able to erase the problems and replace those points by good ones and do that by hand, because I couldn't trust anything else. I just wanted to tinker with the data, make it look good, and then I'd believe the results. And I mean, just think about dropping a binary digit. Even though we were using gray codes and so forth, you can still get some pretty radical problems. Later on, we did, in fact, solve all this by an initial data processing program that would make a good run out of almost pure noise automatically. But in any case, all this stuff was very essential to making this very complicated system work. So the next slide, the next slide, right, is what resulted. This is a program that I called the Scope Input Program. Again, this is August of 1954. It's actually the opening paragraphs of my written talk. And it was one of the few programs I ever wrote that worked the first time. Had about 200 instructions in it. Here they are. And the idea was that I would, we didn't have light pens then. We only had the light cannon and the light gun. And so my idea was that I would track shadow instead of light by a program. And so here's the logic of it. You put down a 5x5 array of dots, top to bottom, left to right. And after putting out each dot with a RC command, here's one RC that is followed by an RD, the light cannon reads that and says, did you see that? And if the light cannon saw the spot, you'd go on and put the next one out. As soon as the light cannon didn't see a spot in the array, you'd recenter the array around that and start over again. And so this little tracking spot, this little array, would go tracking around following whatever motion a pointer made. Now, I'm also going to correct this in the book version, but in the proceedings, I made an error. Never stop being a programmer. You never go out of debugging mode. I thought I found an error, and I corrected it in the proceedings you now hold. The correction is wrong. The old book was right. So in any case, that was my idea for the scope input program. Now remember, I used to take over control of the whole Whirlwind and run it from that main console in room 222, while leaving the regular operators standing around drinking coffee and talking and so forth in the other room. Now at the same time, that upper scope that was in the test control that I pointed out was slaved to follow all display lines. They had something like 20 display lines, 16 display lines, I can't remember, and they all would be slaved together on that upper scope as a monitor. And also, we always debugged our programs with the computer audio on. Now remember, Whirlwind, when I started, we had 1K of memory, 1K of 16-bit words, that 2K bytes. It was so fast, did 20,000 operations a second. That's why it was called Whirlwind. But notice also that made sure that everything was in audio range. And so by hooking a loudspeaker onto a bit in the accumulator, every time the bit changed, you get a bip on the computer, and you would debug your programs by listening to the loop structure. And we did. And so when I took this program that I'd written off to the room 222 to try it out for the first time, I just left it sitting in the photoelectric reader, and I was going to start it up and run it from the other room. As I came into the other room, I says, my gosh, I forgot about it. You remember back there that light cannon was about 10 or 12 feet behind, off in the corner of the room, because it didn't need a person to run it. I forgot to tell you what that was for. The light cannon was there in the Cape Cod system for an area discriminator. What they did was they put down a circular disc of yellow plexiglass over the scope that was mounted horizontally, so its surface made a flat surface, and they'd cover up the middle of it with the circle, but leaving an annular region around the edge, which is the only place that the light cannon could see, so that any airplane track coming in across the boundary would be brought to the attention of the computer, which would then give a buzzer and call it to the attention of a track initiation monitor, and somebody pick it up with a light gun and track it through the system. And what I had seen flying back from Florida was that if I took the yellow plexiglass disc off the inside, I could make my pen tracking program with the light cannon and the scope as I've described. The trouble is it's 12 feet away from the start button. Would I have to call and somehow coordinate with the operators in the other room to actually try my program out? But as soon as I thought of that, I saw the answer. The only reason I expected my program to work was that in fact that logic of left to right, top to bottom, putting out those dots, means that what you actually have is a maximum seeker from the left. Now whatever shadow is in the way of that thing, it'll hill climb just as fast as it can up to the top, and then it can't go down the other side by its logic. So it'll just sit there on the maximum point of whatever's making the shadow. I said, my problem is solved. I walked over to the light cannon area discriminator, took off the plastic disc, put down a piece of paper at an angle, walked back, pushed the start button, walked back over to the light cannon, and sure enough, there was a spot sitting there on the top of that corner. And I very carefully moved my finger up in the shadow while I pulled the paper away, and there was this little square of light, about a quarter of an inch square, sitting on the end of my finger. I started to write my name freehand. And that's what got the attention of the operators in the other room, because they heard this weird scrambly type sound coming out of the loudspeaker, looked up at the scope and saw my name coming out. And he says, my God, what kind of a program do you have there? And so from there on, that was, I believe, the first hand-drawn input to a computer. Well, it turned out, again, because we had later on did this fancy IDPP program, that data processing program that would make a good run out of pure noise, we never had to use this. But we used it in some demonstrations, and it was influential after that, I think. Next slide. That's too long probably to tell a nice story that I like. Anyhow, that was in the fall of '54, and to get back to the personal workstation idea, we had, by that time, done some integration of the push-button control of the displays, intermediate displays of data that would be coming out at different stages of the data reduction. This was a cutout of an actual fighter profile for also putting on with the light cannon to compute probable number of hits on the target. And the important thing here is that on March 8th and 9th, I believe, of 1954, we held a symposium on fire control system evaluation at MIT and had about 150 people come. Now, the other thing that was interesting about this yellow page, even though you can't read it too well, are my handwritten instructions to Dottie Hamilton, one of my programmers, to making up what was called the director tape. The next slide shows that. Now, you see, this is getting into what is required to go along with the workstation equipment on the software side in order to provide the framework so that the personal work can work with it. Well, this is what I claim is the first example of a real operating system. Because what I discovered when I was reading up about what had happened when they shut down Whirlwind, I discovered that not only was the Flexowriter sitting there in the control room, but the mechanical tape reader and the mechanical punch were still hooked up, even though they weren't used. There were wires going into the computer where they'd been the primary input and output system before they put on the photoelectric reader. And so I asked John Frankovich and Frank Helwig, who were at the computer lab, if they would write a program and design a little language so that all the complicated button pushings that we needed to do to load up our programs. By then, Whirlwind had its electrostatic memory doubled, and even that had been replaced by core memory. So Whirlwind was now running 40,000 operations a second, really, really speeding along. And it also had, they put in a magnetic drum. And so here were some instructions for loading tapes and programs onto the magnetic drum. And the rest of these were instructions for reading and starting the complicated restarts and so forth to get different stages of the program brought in and fired up and initialized and then run. So this director tape program was typed out on a punch tape and put in the mechanical reader, while all the main programs of that were to be processed were spliced together in a big roll to be read through the photoelectric reader. And that way we were able to get reliable input for this very complicated program. And it, in fact, because it was also doing storage management, had all the attributes of the job control language of an operating system. Now, in fact, for the demonstration, we had two groups of 75 people coming through to see the programs that we were running with the displays. We slaved together all the displays in the room so that everybody had a good look. And the first group of 75, this worked fine. We had the director tape. We put all of our programs off, in fact, on magnetic tape, and it worked like a breeze. Second group of 75 people come in. The magnetic tape broke down. So I gave the microphone to John Ward to do as well as he could, entertaining them, while I rushed downstairs, got all the paper tapes by hand, and we did the whole job and got the second group through doing it by hand. But in any case, this was what we were demonstrating was the actual interactive use, the choice of what would be processed, what would be displayed, what programs would run for the first time through in a general purpose program. Any problem would have done. We were just doing our evaluation problem. Next slide, please. This shows the sample plot that we were doing at that point. I think it's actually from a little bit earlier, but Whirlwind then had both a point plotting capability, but you could also sweep the spot in the any direction as a vector, which was appropriate for tracking airplanes, but you can see it made sort of spotty grids and spotty lines, but that's the level of output that we had going at that point in time. Next slide. Now, our purpose of the meeting was that we were supposed to be working out our whole data gathering and data reduction methods to be used down in Florida at Eglin Air Force Base, where they were going to have, they were just installing, I believe it's serial number 2 of the 1103 computer from ERA. The first one went to NSA. And so this shows the documents that I'd gotten early in I think it's December in 1954, November 54, about the 1103 computer, getting prepared for that. And our demonstration symposium was so successful that they asked us to do another one just on the data reduction and digital instrumentation problems. And so June, we had the first symposium in March, the second one came in June on that particular subject. Now, in preparation for that, we needed to have the same kind of manual intervention equipment put down in Florida. And so we were focusing on how to do whirlwind type of interaction with the 1103 computer. Next slide, please. Next slide. And in preparation for the second symposium, I got myself introduced to the memory test computer, which was another one that Gordon had mentioned. This here over here, in fact, is one of the original Forrester memory stacks being tested by the memory test computer, which was much like Whirlwind, but much different in packaging as they made progress toward how to ultimately design the ANFSQ7 and later the TX0 and TX2 with the transistor design. But this was the memory test computer, and at this point, after the memories were all checked out and put on Whirlwind, they'd made another memory, and they were using it at this point to check out and learn how to operate the Charactron display tube, which had masks cut out and could display whole characters at a time with a shaped beam. And so that was the display tube that I wanted to have for use in Eglin. And so I wrote a program, next slide please, for this June symposium, and here's the program. Yeah, I guess these didn't really come out too clear because I used to use pencil in those days. But here you can see that I was drawing a little map of the coast of Florida with some islands, and I made a simulation program of launching missiles for testing out of Cape Canaveral. And the simulation program showed where would the pieces fall if you pushed the destruct button now. I thought it would be nice to miss the islands, you see. And then here were displays for making the Charactron use too. And so I like to think that the fact that we demonstrated this in June of 56, whatever it is, influenced later on all the mission control stuff. We did have people there from the Cape, but nothing happened there for another 4 or 5 years, and they never got back in touch with us directly. Next slide, please. And then here was the documentation from that June symposium showing how we were describing the Whirlwind Thyrotron circuits that were used for the activate buttons, which were one shot, versus the intervention switches, which always held their value, and that sort of thing. Next slide. Now, that then completes the portion that I was able to cover in the paper concerning the workstation environment itself and how we started to use it. As this shows, I gave a talk on Gestalt programming, a new concept in automatic programming, at the Western Joint Computer Conference in February of 1956. That was my first professional paper. And next slide, I can show you what the main idea of it is. Here we had in cartoon form a man with an idea, his light bulb, interacting with our type of console through the computer, which gets the idea, and then the computer gets its idea and rings an alarm, and the man's idea is shot down. But the main idea was that we wanted to have not just two-way communication like that, but actual conversation between the two, so that as a team they could work together on solving the problem. And in the paper, I tried to lay out some of the principles and actually carry through a design. Next slide. Next slide, yeah. Which was, I chose an automatic factory where you could have switches, actual toggle switches associated with the different processes and the different flow lines. And here were the verbs: increase, decrease, hold, or reset. You'd get one of those four: the rate, amount, or storage, and so forth. So you can make up whole statements by just pushing those buttons, and when you're done, you can either evaluate that as a simulation mode or execute it, carry it out. And I chose this example of automatic factory control in lieu of one that I also had worked out, which was for launching a satellite. Remember, again, this is 1956, before Sputnik, but I decided that the satellite launch one would be too flashy, and so I settled down to this one, which actually fit better with the app project, which I later inherited, later that year, in fact, although I didn't know it at that time. So again, I'm not going in orally here into a great deal of stress on what it was to envision this generalized use of man and machine in conversation intimately as an actual way of solving problems. But to me, that is the statement of the personal work, the PW aspect, that is the theme, one-third of my theme of the talk. Next slide, please. Now, remember, all that time, this was all being done with push buttons and scopes. There was a flexowriter, but it had never been used as keyboard input to Whirlwind. A lot of people are surprised about this. But as we got fancier in our use and also started some other projects, and I knew that Gestalt programming was what I really was talking about, not just the evaluation program, we needed to have full keyboard input to the computer. By the way, this is the punch here and the reader and the typewriter and the printer part of a flexowriter. So I wanted to have a flexowriter hooked up real-time online as part of my manual intervention console. Next slide, please. And here's a series of memos that I started proposing to put a flexowriter input to the Whirlwind computer. And I originally had thought that I had this all worked out for Whirlwind and proposed and had it in the work before we started working on our proposals for the 1103 console down in Florida. But next slide shows that, in fact, the work for putting it on the 1103 probably came in before I had the idea of needing it on Whirlwind, because I had other ways of doing my Whirlwind work. But here, I want you to just notice that here is the actual console portion of the very large 1103 computer. And see, in fact, it had, this is the top view. There are two sets of boxes making a U shape, and here's the console part right here in the front. And the point was we couldn't modify the 1103 in any way. So the next slide shows my original sketch for how a Charactron with banks of switches as we had on Whirlwind and indicator lights and push buttons, along with an online flexowriter, a tape winder, and a photoelectric reader and a high-speed punch could all be worked around as a man-machine manual intervention console of general purpose to work with the 1103 down at Air Force Armament Center. And we, in fact, actually had this built by Stromberg Carlson who were by then had the Charactron business. Next slide, please. Oh, this is impossible to see in this light, isn't it? Anyhow, that's a drawing of how the online flexowriter was hooked up to Whirlwind and to the 1103, all done with relays. Next slide, we'll forget that one. But the reason this is the corner of it, and down here it shows February 27th, 1958 was when it says, see either Lou Norcott or Doug Ross, okay. So it was in February of 1956 that this happened, and notice that that's before a lot of the other work. And again, that took me by surprise, but really shouldn't have, because as the next slide shows, again, I'm going through these sort of rapidly here, they come out better in the paper, I think. This is a shot of the control matrix of Whirlwind. And I really do hope that someday we can get this rebuilt in actual 3 dimensions, either at the Computer Museum or down at the Smithsonian or something. Because the really neat thing about it is right here, along this edge of this is just one portion of the computer itself that you walked inside, you see. But right here, going vertically, are 5 bare copper wires. Branching out from them at right angles, making a matrix, that's why it was called the control matrix, are 32 bare copper wires that go through these amplifier type and pulse shaper things, and then continue as bare copper wires along this whole wall of the room. Over in this area are 120 vertical bare copper wires that each one terminates in a CPO, a command pulse output unit. Because down at the bottom here are 8 coax lines that carry the time pulse from the time pulse distributor of Whirlwind. And what fascinated me about this always is that right here in this matrix between the 5 vertical and 32 across, you would see soldered right there before your very eyes the binary number system. That was the decoding of the order code into one of 32 lines. And then to understand the order code of Whirlwind, you could take each of these and read the soldered in diodes to see exactly which steps took place on which time pulses. You understood the whole computer just looking at it. It was right there, beautiful. Well, the neat thing was when, next slide is fine. When they shut down Whirlwind to put in the magnetic core, which was essentially overnight, it turned out there was a whole program register, so-called, a 16-bit register with gates and everything, hundreds of dollars a bit, sitting there, still in the computer, not hooked up to anything. It was not needed anymore. When I discovered that, I decided, wow, I wanted to get some microprogramming going on Whirlwind, where I could make up my own order code and do much better Gestalt programming and handling input-output than using the standard 32 bits, 32 instructions. So sure enough, I worked out a whole set of logic for redesigning Whirlwind so that you could throw a big gang switch and either have my new MI microprogramming instruction in or out of the order code in place of one of the other instructions. The only trouble was we never got to putting it in, because when I wrote some test programs, writing standard Whirlwind versus designing the best microcode I could for several little applications, each time it was just about a standoff. And the reason was that there were no excess logical paths at all in Whirlwind. Everything had to shuffle through the A register, which acted as a buffer to the accumulator and memory and every other darn thing that went on, and it was a bottleneck. So although this was a step in my trying to get that hardware-software combination of how to make personal work and workstation linked together, it too never came to anything, just as we hadn't actually had to use the scope input program. Next slide. Oh yes, this is just writing up the Whirlwind methods for the design for manual intervention consoles. This is John Ward's writing here. He's an engineer, I'm not. And together we wrote, next slide, this document, which is the final memorandum that was the specifications for making that first general purpose machine console for use at Eglin. Next slide. And just to bring things up to date, this is 3rd of October 1956. I believe these are John Walsh's handwritten notes for how to set stuff in the LIP, the left insertion panel of the console in room 222 to run our programs. Next slide. And this is the much improved, labeled and cleaned up. Notice the scope itself is working better these days, but also our software is keeping up with it. That's an actual piece of misdistance calculation from our evaluation programs in May 9th, 1957. Okay, next slide. Now, I'm just going to wrap up this talk briefly by talking about SLURP. SLURP was Servo Lab Utility Routine Programs. And it's the backbone of all the stuff that allows the hardware and software to come together and allow you to design special purpose man-machine interactive languages for use with your arbitrary problem. In other words, SLURP was in my mind what the Gestalt programming, the name never caught, the ideas were hard to catch in those days, but SLURP was my idea of what Gestalt programming had then evolved into, this idea of the intimate workstation. Next slide, please. This is just more close-up of the thing, but here are the features that we had in the SLURP system. Now remember, this was, at this point, they had upgraded the core memory, adding 2 more banks with a bank switching instruction, so we in fact now had 6K words of storage. That's 12K bytes. I mean, wow, you can do anything with that, right? And especially, they didn't change the drum at the same time, though, so we only had 2 or 3 times as much space available to us on the backup drum. So you figure yourself, we're working maybe with 40K bits total, or bytes total to do this. Well, what we had was a full group control program which allows the automatic incorporation of new sections of programming into the system. This worked with virtual storage, dynamic storage management type things. We had a full manual intervention system which allows what I've been talking about. We had a logging program which records all the MIV actions taken by the programmer during a run. Yeah, that would be punched out on the online punch. We had an editing program which edited the login information so that both for printout and for a log playback program, and the log playback program could automatically reproduce any of the manual actions. And you also could use that at the first place to run the programs just like their director tape programs. And we had this elaborate set of plotting and tabulating programs for data presentation and recording, both graphical and in terms of characters. And then a thing that I've skipped over here in this oral talk was the mistake diagnosis routine that I'd done earliest for this. This is where all the drum swapping for groups and group control and so forth originally came from. You could put interruptive breakpoints into any point of any program as long as you had something like 26 spare registers to put a bootstrap in. And you could then get graphical or full manual intervention, graphical or typewritten displayed information from any places in any program. And again, all of these things were online under control of manual intervention. And the key thing was the SLRP program proper, which is called here, which was a simulated computer, which has many of the attributes of the B5000, as a matter of fact. It was able to control all of these things. And it was also sort of an interesting thing in that it had a multi-mode control element so that you could jump around and execute instructions at in different modes of behavior. There were actually only the A, B, and C mode. A and C mode separately, and B was both of them together. But the neat things that you could do with that were manifold. In particular, the SLRP instruction set for the simulated computer included the FlexoWriter characters, our version of EBCDIC in those days, you see, or ASCII. Those characters codes themselves were part of the instruction repertoire of the computer. And whenever they came along, they would be put out on whatever display device was then hooked up. And so by using the multi-modes of control, we could have both abbreviated labeling for displays and full-blown labeling for printouts and that sort of thing. But you also could use the same thing to get very exotic program behavior if you, instead of working with characters, you worked with other SLRP instructions. Now the key thing that made all this work, and this I claim is the earliest version of what nowadays shows up as the debate of how many buttons to put on a mouse, okay? This was the MIV box. Guess what? Manual intervention box. Very imaginative. But here it is in flow diagram form. In order to obtain control over these very elaborate programs, and also in a way which would serve as a framework and architecture for general purpose use, everything was designed to be very modular and had a hierarchic control structure. So with just two activate buttons, a major activate and a minor activate, and two switches, a wait switch and a cycle switch, you see, and here's minor, minor, major, major, and so forth, and this idea of the MIV dispatcher, which was the place where you read all the other push buttons, including the keyboard. By just using major, minor, cycle, and wait, we were able to have full control, provide a full language framework for designing new Gestalt languages to go with the SLRP controlling of the SLRP system. And in fact, the next slide shows how this MIV box is here used twice. Here it is once, and here it is again, with various controls, loops going around to take another switch now that we call a plot switch, another switch called the data switch. So two more switches, you see, just two switches, along with two calls on the MIV box, gives full control over which functions to plot, which frames to plot of all the functions that showed up in our elaborate data reduction program. And of course, with one more switch, you could control whether it was done online or offline. So with three more toggle switches, that with the standard major, minor, cycle, and wait would give you complete control over that whole system. And so again, as a form of language design, a few stages up from the basic ideas that I'd had at the time of writing the Gestalt paper. I should also point out here in the oral part, I think that one of the earliest things that came when I had to rewrite Bill Wolf's original manual intervention coding that he'd done for me, he had worked with the then extant version of our evaluation program and had embedded all of the SI and RC and RD instructions for reading and recording and selecting the switches and buttons. He'd embedded those right in the points of the evaluation program where the information was needed, as was done in the common practice in the programming of the Cape Cod system for air defense. Well, that wouldn't suit my purposes at all. So the first thing I did when I rewrote those things was I made a separate reading process that would read through all the switches and record the values of things that were available in variables, so that all my software then worked off of variables. And that was a crucial step, because you see that's what made possible the automatic logging and playback of all the rest of the Slurp features. In other words, this very primitive idea of separating the concerns, later on we would call it that, came as a direct requirement of wanting to do general purpose things with what had originally turned up as a special purpose style of use of special purpose MIV hardware. Next slide, please. Yes, I've got about three more to rush through. In fact, we'll skip that one. This just shows how late, what I'm trying to do now is I finished all my talk about what goes with the 50s directly, and I've just got a few slides I'd just like to couple in with Gordon's stuff to show what happened. Here was the actual light pen, developed at Lincoln Lab, but refined by Servo Lab, Electronic Systems Lab, to have lens system and focusing. Next slide. Here was the light cannon with its power supply and photomultiplier tube, and push buttons and indicator lights for hooking up to the IBM 704, 709, 90, and 94. That's the one that was in the works when Ed Jacks came by. Next slide. Here is How to Speed Up Invention, November of 1956. An article appeared in Fortune magazine by George Price, which was the real precursor to all of the CAD-CAM type workstations, because he had our kind of push-button languages. He has the scope. Later on, our ESL Display Console, as you saw in the movie, did these rotations online. George Price was an interesting guy. He stopped by at my house one time after I ran across the article, but he wasn't all that deep into the area, the technical area, so we didn't get too far, but it really is another first in the 50s, and one that's fun to look up and read about. Next to last slide, I think, is the ESL Display Console, which you've seen already in action with Charlie Lang there at the Mighty Wurlitzer with the crystal ball in the middle. And do I have another one? Next slide. Oh, yes. Also out of this was by the time this came along, you see, we were working in the computer-aided design project doing all this work, and John Ward was heading up the display group, and we were tied in with Project Mac and so forth. Well, Rob Stotz also did the first of the storage tube display systems. This is the ARDS, actually ARDS 2, but showing the high resolution that was possible on a bitmap display with a memory storage tube. So I think that is the last one, is it not? If so, we could have some lights. And in sort of a rushed, haphazard fashion, again, what I've tried to do is just be me and let you have a bit of a feel for how it was to actually have been there. I do a better job in written form always, and I hope you will enjoy reading the paper. In any case, it's been a great pleasure for me to be a participant here and to have your kind attention. Thank you very much.
Okay, what I get out of all of this is the feeling that you actually had to be there, a traditional thing, and you had to be familiar with the kind of equipment that people had at that time. I think Doug's comment about 1K of memory and 20,000 operations per second was really awesome in those days. And I remember actually when I was working on the communication between the sectors in the SAGE system, we had 1 kilobit lines interconnecting interconnecting what was called the direction centers, and the problem was to figure out what to do with that 1 kilobit. It seemed like just an enormous amount of communication capacity at that point. I guess I have one question, and we were standing and talking to Al Newell in the break here a few minutes ago, and we were talking about what it is that makes new ideas come forth, and I'm really curious about that. I think we all are. and we were talking about the connection between sort of existing hardware, existing technology, and new insights. And you made some comments at that time that I think are interesting, and I'd like to ask you sort of to repeat them here for the people. That's one question. And the other question is, of this sort of array of novel ideas here, I'm curious to know which you think are say, the three most influential ones. I heard a number of things that were originated here, and I wonder what you think are the three most original ones, or most important ones, I should say.
Well, I'm really not very programmable, so I'm not sure how I can reproduce what we were talking about with Alan. But the idea is that I have about where creative insights come from is that it's somebody who actually is there in an environment that's built by, in terms of whatever that day's technology is. And what you do is that individual sees through, but sees reflected in. In other words, you sort of penetrate into and have it reflected back to you what really is going on, what really is implied by what's here. I don't think there are very many things that are really dreamed up completely out of the blue. I mean, some artists maybe, but I think that's more that they have a slightly demented mind and are doing just the same thing with a warped set of filters, you see. I mean, you need to have a reality in which you are a participant. And then what makes the innovation is this deeper insight, literally seeing into, but reflected back to you, what is your current total situation and environment. And of course, because it's always not what's on the surface, but something else, there's inherently a built-in level of abstraction that has to go along with it, which is why you do get the ideas that are portable. You see, they carry around and can apply to many things. And of course, that comes across when you formalize it, when you talk about it. Wow, that's a brilliant idea. That's a great generalization, you know. But it really is just this thing of a little bit deeper version of the same kind of seeing and interacting and participating that we do all the time for everything else. As to the top three of what I would pick out from what I was talking about, I think I'd rather leave that to you all, or later historians even, because again, I've never been able to track down who actually saw or was influenced by the things that all I know is I was there, I did them, I remember them vaguely, I found them in my materials, I've documented them here for you in a rather sloppy fashion, right? But they did happen. How they then permeate and get to influencing other people, I don't know. All I know is that all during the years of my having very creative people working with me, mutual stimulation, again, the same thing of it's the environment you're in, you see, and the problems you're given, the challenges. We always had to have problems that were needed yesterday, not tomorrow, but yesterday. We had to have real people asking for real solutions in problems that were beyond the state of the art. So we had to do that penetrating and getting further. And then when you get a creative bunch of people in such an environment and get the right general way of doing it, you come out with a whirlwind. You come out with Wes Clark's paper. I just loved to read that last night. You'll just love, he does a much better job of showing what it was like to be there and have the people involved. My memory doesn't do that. I have to work with my old stuff. But anyhow, I think that the main thing is that I was aware, because of this insightful look, from the very beginning, after I first walked into room 222 and had that, wow, that whee, look at all those green scopes, a red light, whoo, I mean, real, if they only had a laser light show, that was the version in those days. It really turned me on. I knew that's what I had to have. And immediately I saw it in its generalization, because I had already building up in me this vast set of needs for what I thought was and it was true, it turned out to be a very, very complicated set of data reduction programs to do on that little bit of memory. See, the 1103 wasn't that much bigger than Whirlwind.
We got to check about hunger versus curiosity. I'm afraid, I see John nervously over there trying to signal me that I should cut this off. I feel it's unfair not to let the audience ask at least one question, don't you think? One, he doesn't like it. Go ahead.
Okay. I'm Sig Troy, University of Pittsburgh. I wonder whether, from your perspective, you could characterize to what extent the history of personal workstations is necessarily overlapping with the history of what one might consider to be computing or computers in general, or if I may rephrase the question, can you identify criteria by which we might separate out those historical aspects that are peculiar to personal workstations. Because one might argue that some of the things that have been presented this morning could just as well be included in the history of computer hardware and computer software and so on.
I think that probably goes along with the comment that you must have that reality in which you're participating to have any of these things happen. Of course, one of the earliest personal workstations is the cobbler's workbench, right? And they sit there and all the things are right there for them to work with. Again, it's the technology and the problems, the needs of that day is what makes that workstation. And so if you followed through what Gordon was covering in his talk, the key thing that managed to, in our own computer field, make the sweep that gets us up to today's and tomorrow's talks about the last edge of this, what we consider this historic development period. It's the going through the stages of how do you bring the costs down so that you can get the power up to match a broader and broader class of individuals in terms of their problem needs and in terms of their economic needs. And again, the point that John Brackett was making in the comment on Gordon's talk, and it was the line that Severo was bringing out, I thought, and which is the main one that I'd like to stress, it's how you bring those together. How do you bring the PW and the WS together with an architecture and a systematic treatment more than just how to put variables instead of programming directly in line, more than just having Gestalt language idea with switches and so forth, more than having just a slurp system that has the software framework and the building blocks, more than just having software engineering toolkits and languages, more than having nowadays modular software building blocks. I mean, the Occam system, that it takes it right out to the hardware building blocks that you hook together, which is another one of Wes Clark's old pet peeves. Those are just stages of development. And what they do is they manage to reform this reality with which we interact at each stage. And as we understand more and more about it, you find that the man and the machine do, in fact, become more and more coupled. And their view of what problems are and how to go about solving them become more and more sophisticated and more coupled. I think it's really exciting stuff to do. Thanks.